Everyone, we start now the first talk of Clay Cordova. He will tell us about supersymmetries and anomalies.
No supersymmetries, only symmetries. Yeah. Okay. Thanks very much to the organizers for inviting me to give some lectures. So the subject of these talks will indeed be symmetries and anomalies, and I'll introduce you a little bit to the formalism of generalized global symmetries, some of the new things that you can learn from them, and how do you do it. But to start, I'd like to give you some motivation. So some reason to care. So those in the back, please yell at me if I don't write large enough, especially you, Liam. Good. So there's this basic problem in quantum field theory, which is that someone gives you some UV degrees of freedom, and you'd like to run the renormalization group and figure out what's going on at long distances. So this is the basic problem that we will ourselves be interested in, and one of the things we're going to do is we're going to develop tools that can help us solve this really fundamental problem. So what kind of typical examples will we be studying? So typical examples that we are most interested in will be 3D and 4D gauge theories. So of course one can run this in general, but really we'll see that there are new things to say even about extremely basic gauge theory examples. So let me highlight one of them. So let's study 4D SUN Yang-Mills. And here I will mean without matter. So there's a lot of lore about this theory. It's ancient by our standards. So what's the lore? So the lore is that if you start with this theory at short distances, it's of course asymptotically free, and we believe that the IR is gapped and confining. Okay. So let's get a little more detailed. So the action contains a term, which is particularly interesting, the theta term. So this is the famous theta term in the Yang-Mills action. And this here is the instanton density. So with the normalization I've chosen, integral of trace f wedge f over 8 pi squared is always an integer. So you can think of the parameter theta here as a kind of coupling constant that's valued in a circle. So in fact, Yang-Mills theory is not just one quantum field theory, but rather a circle's worth of quantum field theories labeled by this parameter theta. So you could ask, how does the IR depend on theta? Now, let's try and be a little bit more detailed about what kind of possibilities we could envision when answering a question like this. So what kind of possibilities do we envision? So possible IRs of QFTs, generally speaking. Let's make a little table. So the first thing is that you could imagine that the infrared is gapless. So here I'm motivating everything with a discussion of SUN Yang-Mills, but this list of possible IRs really is a sort of general picture of all possible IRs of QFTs that we might want to study. So gapless means that at long distances it's described by a CFT. This could be a free CFT, or maybe more exotically interacting. Now, before coming on to the second point, let's say that at least as a function of theta, we don't really believe, although we don't know, that Yang-Mills theory anywhere in theta becomes gapless. That would be extremely exotic. So this possibility, while it's logically there, this would be exotic for Yang-Mills. But it's not logically excluded by anything that we know. At theta equals 0, we have a lot of lattice evidence that suggests that this picture is correct. But at general theta, it's very hard to simulate this, this system with the lattice, because this, when you go to Euclidean signature, this term becomes a phase. So you have a simulation with a phase, not a positive definite Euclidean action. And that's very hard to get reliable information about. Okay, so that's not excluded for general theta. But the more typical expectation, for Yang-Mills at least, and another logical possibility for general QFTs is gapped. So we said here that this was gapped. What does it mean? So it means that all particle masses m are greater than 0. So in QCD, or in Yang-Mills, we think that masses of particles are greater than the dynamically generated scale, or around there, lambda QCD, which is, of course, greater than 0. That's part of our belief about why the theory is gapped. Now, once we get to gap theories, we can actually make a distinction between two different kinds of gap theories. So boring theories, you might think a gap theory is boring, but they come in different degrees of being boring. So the first that we can say is that we could say that a theory is what's called trivially gapped. And what this means is that it's really empty. So there's the IR is really the empty theory. That means there's no interesting correlators at all to study. We already know that there are no massive particles, and this tells us there's no correlators at all. But there's another subcase, which is that even if your theory is gapped, it could have some topological correlation functions. So it could be a non-trivial topological quantum field theory. So I started by motivating this discussion in the context of Yang-Mills theory. And that's a four-dimensional quantum field theory. You might not know many 4D topological quantum field theories, but actually there's a whole zoo of them. It's an open problem to classify them. So there are lots known. There's no known classification in 4D. So when we're organizing our ideas about what the infrared of a quantum field theory might be, it's useful to have this hierarchy in mind. First of all, the theory could be gapless or gapped. And if it's gapped, it might be a completely empty theory, the trivially gapped theory. Or it might be a non-trivial topological field theory with some long-range correlation functions that are independent of the metric. So what's the more precise conjecture, the more precise lore about Yang-Mills theory in this language? So a conjecture is that SUN Yang-Mills at theta equals 0 is trivially gapped. So that is, at theta equals 0, it is the most boring it can possibly be at long distances. There is not even a topological field theory there. It's really the empty theory. This is not known to be true, but it is widely believed. The lattice evidence really doesn't tell us much about the distinction between these two possibilities. Now, given this, so let's go back here. So here we saw that we have a circle worth of QFTs labeled by this parameter theta, and we've said a natural conjecture at theta equals 0. So you might ask, can the IR be boring, that is trivially gapped, for all theta? And the answer to this question is emphatically no. This can be proven. So there is a result which I like to introduce as a motivation on why we should study this subject. The result is due to, first, Gaiotto, Kapustin, Komorgotsky, and Seiberg, and then also there's another relevant paper by myself, Hotat Lam, and Nadi Seiberg, which is says the IR at theta equals pi, that middle value of theta, cannot be trivially gapped. So one of our goals in these course of lectures will be to build up the kind of technology that we need to understand how you can rigorously prove a statement like this. How can you show that this very strongly coupled Lagrangian nevertheless has some interesting behavior for at least one value of its coupling at long distances? Now, in fact, even more is known now. So let me tell you, even more is known. So what's so special about theta equals pi? So in fact, theta equals 0 and pi are special because they have time reversal symmetry. So let's introduce time reversal symmetry T. It flips the sign of epsilon because only one index on epsilon can be 0 at a time. So the theta term in the action was F wedge F, or in components F mu nu F rho sigma, epsilon mu nu rho sigma. So therefore, T flips the sign of that term. So we can say that T of theta should be minus theta. So what we learn from this is that typically, for a generic value of theta, if we do this action, we don't come back to ourselves. So typically, the theta term breaks time reversal, except for at these two special places, theta and pi, which are fixed points under this, 0 and pi. So 0 is a fixed point, obviously. Pi is a fixed point because theta is 2 pi periodic. So 0 and pi have T symmetry. So we were looking at this special value theta equals pi. And we can also think about the behavior of the infrared theory with respect to this time reversal, because that theory is time reversal invariant. So, possibilities for theta equals pi. Okay, so the first, as in our general discussion, is that it could be gapless. And this would be, as I said before, very exotic. So let's ignore that momentarily. It would be extremely interesting, but it seems exotic. Now, of course, the other possibility is gapped, but now let's think about gapped with respect to this symmetries. So it's gapped. There's a result here that we're building towards eventually in these lectures, which says it can't be trivially gapped. So therefore, if it's gapped, it's a non-trivial TQFT. So there are various features of this TQFT that we'd like to examine. One is that it might be confined. So that's the question of, do large Wilson loops have an area law? And the second question, given that our theory is T invariant, is we could ask about T invariance of the vacuum. So is T spontaneously broken or not? So if we're in the gap case, we'd like to discuss these features. And here's another result. This one is due to myself and Kentaro Omori. SUN Yang-Mills at theta equals pi cannot be simultaneously three things: gapped, confining, and T invariant at long distances. So this is, again, another thing that you can prove. So what's the lore? If you had to make a guess about which of these properties has to give, what do people think? So what people think is that T is spontaneously broken at long distances. This means that there are at least two vacua and domain walls connecting them. Okay, so this is, you're not supposed to be able to understand how to prove any of these statements yet. That's what the subject of the rest of the lectures is about. But I like to give them to you as a kind of invitation. Somehow there's new techniques in quantum field theory that enable us to prove new results about Yang-Mills theory, that kind of most basic interacting Lagrangian that we really want to know a lot about. And for me, this is the main reason to study this subject, is that we can really get somewhere new on a really old problem. So are there any questions about these statements? This is just general lore and also some results. And now I'll get into some more technical subjects.
So you mentioned it's 3 and 4 dimensions. What about other dimensions? 5, 6, etc.
Well, so you can, yeah, so these techniques are very general. They'll work in 5 and 6 and whatever dimensional quantum field theory that you happen to be interested in. The main reason for focusing on these examples is that they're in some sense very simple. You know, if you want to study a 5 or 6 dimensional interacting quantum field theory, you've already got a mouthful just saying what you're talking about. There's also a huge amount of applications in 3 dimensions, though. So I'm ignoring that dimension not for any good reason, just to have a focused case. Okay, so what would be our main techniques here? So our techniques are the title of the lectures, Symmetry and Anomalies. And why these subjects? Well, what we're really going to try to do is develop renormalization group invariance. The anomalies that we're interested in are sometimes also called the 't Hooft anomalies. Unfortunately, physicists are very bad at naming concepts, and we don't give ourselves license to rename concepts later. So there are 1,000,001 things in physics that are called an anomaly, all of which are somehow slightly different. So I'll try to define what I'm talking about. But yeah, so this is the main reason, as we'll see, why symmetries and anomalies are powerful. It's because they are renormalization group invariant notions. So if we have them in the ultraviolet, we must find them again at long distances. And that's really what's going to help us make progress. Okay, so let's first discuss symmetry. So symmetry itself is RG invariant. What do I mean by this? What I mean is very simple. I mean that if you have an ultraviolet quantum field theory with symmetry some group G. So first of all, what does that mean for me? This means that the local operators are the thing that define my quantum field theory. And I'll say that the local operators are in faithful representations of G. Well, let me erase this word for now. Let's say representations. So this is what I mean when I say that a quantum field theory has symmetry G. I mean that you find it acting on the local operators, organizing correlation functions. Now you run your RG, and you get to the IR. And the same thing must be true. So the IR has symmetry G. And again, one finds that the local operators are still in representations of G. Now, there's a small caveat here that I'd like to bring up. So here I focused on the action of symmetry on local operators. And you might have asked, why didn't I think about the Hilbert space? You often think about symmetries acting on the Hilbert space. So saying that the Hilbert space is in a representation of G, at least if you're talking about the Hilbert space in flat space, is not actually an RG invariant notion because of spontaneous symmetry breaking. So the IR Hilbert space in infinite spatial volume may spontaneously break a given global symmetry, but always, 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 the local operators stay in representations of the global symmetry. So symmetry, defined in this way, is our first notion of a renormalization group invariant. If we have it in the ultraviolet, we must find it at long distances. This is useful, but sometimes not so powerful, because at long distances, the symmetry could act trivially. So this is useful, but might not act. So what's the simplest example of that? I'm sure you're all familiar with many examples. You could take a massive complex scalar. So this, of course, in the ultraviolet has a U1 symmetry, which rotates the phase of the field. But in the IR, it's trivially gapped. This means the only operator we can really study at long distances is the unit operator. Now, of course, the unit operator is in a representation of U1. I didn't violate my general slogan here. But it's in a very boring representation. It's uncharged, and there are no charged things at all. So here we see that if you just think about symmetry as an RG invariant, it's true that it's RG invariant, but there's nothing that's guaranteeing that at long distances it acts non-trivially. So what you might want to know is, are there any circumstances under which we can be sure that the symmetry will act at long distances? Now this turns out to be a pretty deep question, and the answer is basically this second sort of RG invariant, the so-called anomalies that we're going to talk about now. Questions? Okay. Okay, if we want to understand better the details of global symmetry, it's helpful to couple our theory to sources. So these sources will be gauge fields. What does that mean? So we'll probe a theory with global symmetry by coupling to a background gauge field. So my background gauge field will always be called A. And what does it mean? It means I'm going to include in the action a term of a standard sort, d to the dx, a mu, j mu, where here j mu is the conserved current operator. Now, in this discussion, A will be a classical background gauge field. That cannot be stressed enough. What that means, the word classical here, means that it is not summed over in the functional integral. So A is introduced as a classical source that couples to J, but we do not do a path integral over it. We do a path integral only over the quantum dynamical fluctuating fields, not over A. So the integral over fluctuating fields not A, this leads us to a partition function z of A. Since we did not integrate over A, since A is classical, A is an argument of the partition function. So, of course, we've all seen this before. And when you've seen it, it's likely used as a trick for organizing correlation functions. And so that's actually a good way to think, at least at first pass, what is this object z of A? So it encodes correlators. Correlation functions of the conserved currents. Now, in these kind of correlators, J mu is conserved. We saw that here. But there's a subtlety. So we know that J mu is conserved when the xi are distinct. That was actually what we meant when we said that J mu was a conserved operator. It means that in correlation functions, the divergence of J is 0 as long as the point that it's inserted at does not hit any other points. So we should ask, what about contact terms? Now, there's an equivalent way of asking about that in terms of this partition function. So equivalently, we could ask, is z of A plus d lambda equal to z of A? Why is it equivalent? Well, if I shift A by d lambda, that is, do a gauge transformation on A, that's like activating the divergence of J. So if A is d mu lambda mu, if I move the d over here, it's like lambda is a source for the divergence of J. And so if really the operator J mu is conserved even at coincident points, then I should have this equality. Are there questions about this logic? Okay. Now, in general, that equation is not true. In general, it is not the case that a z of a plus d lambda is z of a. So this is like a gauge transformation. But on the background field A, in general, we find the following. Okay, let me unpack this equation. So here we see that there's a correction term, first of all. The correction is controlled by some object omega. And the important point that we should remember, the really key point, is that omega of a and lambda is local. That means it can be written as some kind of polynomial in derivatives of in A and derivatives. And the reason I know that is because I know that J was conserved at separated points. So this kind of term is allowed because that is a local term in A, because that is a correction that is correcting only the contact terms. But if there was something non-local, it would be correcting even the separated points. So this is really key. So the only kind of correction I can find is something local. This is because it can only modify contact terms. Okay, now while we're at it, you might say, well, this looks quite silly. After all, when I was studying my partition function and my correlation functions, I wasn't so specific about the counter terms anyway. So you could try to adjust the definition of z to remove omega. What does that mean? We could try to redefine z. So here's our old z. And instead, we take it to a new z of the following form. So, importantly, just as omega was local, here f is also local. And the reason it is local is for the same reason. I am allowed, when trying to define my quantum field theory, to choose a scheme for my contact terms. I'm not allowed to modify any separated points information. That's intrinsic to the theory. Choices of contact terms are not. So such a modification, that is, adding an f there, will change the contact terms. It'll change what happens when j's hit each other, but it doesn't change any separated points information. So this is a kind of intrinsic ambiguity in the definition of a QFT. So now we come to a key definition. So if omega cannot be eliminated by any choice of f we say there is an 't Hooft anomaly. So this is the definition of this term, 't Hooft anomaly. So the invariant information is the kind of equivalence class of omega. That is omega modulo all choices of f that we could try to do to remove omega, to remove this pesky gauge non-invariance formula. So obviously such things, the set of possible omegas in general is classified by a kind of cohomology problem. Okay, so everyone has probably seen something like this before, but to ground you in a basic example, so basic example in 4D QFT are the examples that come from triangle diagrams. So we could have, say, Weyl fermions. Psi alpha. Let's give them an index I. Some charges Q sub I under a chiral U1 symmetry. That just rotates them all by some overall phase. This is probably getting too small to be seen. And from evaluating this kind of Feynman diagram where you have 3 J's inserted, you find the famous formula that the divergence of the current goes like sum over I qi cubed Fa wedge Fa. So this is equivalent to the kind of thing we've been talking about before. So here it's the divergence of the current in the presence of a background gauge field. Depends on that background gauge field. So if we wanted to write it when the background gauge field is off, it's a statement about the contact terms. In the 3-point function. So this thing has a term that goes like delta of x minus y, delta of x minus z. Correspondingly, the partition function in the presence of a background gauge field is not exactly gauge invariant. There is this local correction, the anomaly. Okay, so why care about anomalies? As I've defined them so far, they seem mostly like a nuisance. And what I'd like to do for the last part of this lecture is to convince you that anomalies are very useful. So what we're going to try to sketch is the basic reason why anomalies, as we've defined them here, our renormalization group invariance. So I'll give you kind of a bit of a hand-wavy, sketchy proof, but it contains sort of the kernel of an argument. There are actually lots of ways to prove this, and it's really only when you see 3 or 4 together that you start to really believe that it's true. But here I'll give you one. So let's consider Z, our famous partition function. It depends on our background gauge field A. And let's also introduce G, where G is a metric. So we can consider a transformation. So we can consider G going to e to the sigma times G, the breathing mode, if you like. And by scaling up sigma, I'll probe long distances. So we'd like to understand how does the anomaly behave under changing sigma. That's really our question. So we use now the so-called Wess-Amino consistency condition, which sounds like a very meaty, non-trivial thing. It has 2 people's names attached to it. The Wess-Amino consistency condition is a statement about partial derivatives. And it says something extremely simple. It says that, first of all, if we take d sigma of d lambda of log z of a, well, let's just put log z, that this should just be equal to d lambda d sigma log z. So the Wess-Amino consistency condition is this equation. It just says that you can treat log z like a function and take derivatives, and it doesn't matter which order you take them in. Okay, I won't hate on the Wess-Amino consistency condition too much. So what is this? So d lambda of log z, this is our anomaly, omega. So if I take d sigma of that, this is the scale dependence of the anomaly. So that's the thing that we wanted to constrain. What is the right-hand side? So if I take d sigma of log z, well, sigma is a change in a background metric, and varying with respect to the metric induces the stress tensor. So this is d lambda of the integrated expectation value of the trace of the energy momentum tensor. Trace because I did a Weyl variation. Now, I claim that you should think that this is usually 0, or maybe always 0. And why is because it's asking if the stress tensor transforms under gauge transformations. That's what delta lambda of this would be. So this is 0 because the energy momentum tensor is gauge invariant. So as for this is a kind of sketch of an argument. There are some loopholes in it, but the conclusion is correct. Anomalies are RG invariants. And it's for this reason that we care about anomalies, because it means that if you find some anomaly in the ultraviolet, it has to be the case that you find it again in the infrared. And that's really the basic driving force under those new results about Yang-Mills theory. So to conclude, let's connect this discussion to our previous analysis. So Z of A, what kind of function is it? Well, it's typically a horribly non-local function. That's because the separated points correlators of J's are non-zero, typically. Remember that you think of Z of A as a generating function of conserved currents. Taking derivatives with respect to A brings down J, so it's the non-localness of Z of A that is responsible for the non-trivial correlators at separated points. The local pieces that we focused on before are just affecting the contact terms. But generically, this is a non-local function. Now, if our theory is trivially gapped, so if the theory is trivially gapped, the only operator that is allowed to have non-trivial separated points correlators is the identity operator. Right? A trivially gapped theory was the empty theory. It meant that the only non-trivial operator was the identity operator. So if a theory is trivially gapped, then Z of A should be local. That's because we want, in that case, all correlation functions of J to reduce to contact terms. That's what it means for J to vanish as an operator. Its correlation functions reduced to contact terms. So in this case, we could write that this is equal to something of the following form. That was our generic expression for something local, where here F is a product of A's and derivatives. So local. So this is the case if a theory is trivially gapped. Now, these kind of actions, where you have something that's purely local, just something that generates contact terms, they have a lot of different names in the literature. Sometimes they're called invertible theories. Sometimes they're also called symmetry-protected topological phases, if you're a condensed matter theorist. Sometimes they're called counterterms. And sometimes they're also called classical field theories. Classical field theory because A isn't fluctuating. We just have an action for A where A is a fixed variable. So all of these terms are synonymous. So if you encounter them now, you know what they all mean. And which one you choose to use kind of brands you as a theoretical physicist, or you could be a mathematician, or a condensed matter physicist, or a high energy physicist, or I don't know who uses that one. So here's what's going on for Z of A for a trivially gapped theory. It is local. And we saw that we had a definition of what an anomaly was that also involved these local counterterms in a crucial way. And if we put the two together, we get the following important statement. A trivially gapped theory has no 't Hooft anomaly. Why is that? Well, we see that a trivially gapped theory has this kind of local form for its partition function. And we also saw that anomalies were only defined modulo such shifts by local functions. Now, if we combine this with the RG invariance of anomalies that we discussed, we get a really basic fundamental conclusion, which is that a UV theory with non-zero anomaly cannot flow to an IR which is trivially gapped. No, on the contrary, since we have a non-zero anomaly, the IR theory, whatever it is, must reproduce that anomaly. It cannot, so the partition function cannot take this form in the long distance limit, and the theory cannot be trivially gapped. So this is really the basic kind of fundamental conclusion where a lot of that discussion about Yang-Mills at the beginning comes from. That's because we'll eventually be able to exhibit some new kind of anomaly for Yang-Mills theory at theta equals pi, and hence we'll get this conclusion applied to that theory. Okay, I'll stop here.
First, let me remind you that we will have a discussion session later today, so please think also for questions for this and for topics to discuss for that session. And now, short questions now. Long questions also. Maybe we can. So here in your argument, so this one-point function is a one-point function in the presence of the sources, right?
Right. That's why there's a loophole in the argument.
Exactly.
Is because usually we think that the stress tensor, certainly without the sources, should be a gauge invariant local operator. And now I'm asking the question about the stress tensor in the presence of sources. So that's why I don't find this argument to be sort of the most like 100% lockdown proof, but it is very suggestive. That's why I bring it up.
Okay, well, we'll ask you more questions later today. So we have a lunch break now. We reconvene at 2:30 here. Thanks.